webinar on machine learning and robotics to scale climate action. I'm Amanda Parizenti. I'm a core team member at Climate Change AI. We are delighted to welcome everyone joining us today across countries and time zones to attend CCAI's webinar with our speakers, Serena Mu and Marius Wigert. Before we dive into today's presentation, I want to briefly introduce Climate Change AI. We are an organization that seeks to catalyze impactful work at the intersection of climate change and AI, a worldwide network of researchers, policymakers, volunteers, and other stakeholders. CCAI is also a curator of digital resources. We provide advice for relevant stakeholders and host open events like this webinar for knowledge sharing. We also run a number of events at various climate and machine learning conferences. You can find recordings of these events online at climatechange.ai/events. You can search through all of the accepted papers at CCAI events on our website too at climatechange.ai/papers. I particularly encourage you to check out this panel that was co-organized by CCAI at COP27. It was focused on open data and artificial intelligence for actionable climate action in monitoring, reporting, and verification. This event took place yesterday as a COP27 side event and was organized by Climate Change AI, Gain Forest, and Transition Zero. Climate Change AI core team members David Dow and Priya Donti were speakers at this event. You can find out more information on this panel as well as watch the recording via the links you can see on the screen now. If you want to exchange ideas with people interested in this intersection of machine learning and climate change, you can connect with a wider community on our community page. We also have a directory where you can add yourself if you are working in this area and search for other people engaged in similar topics. We also have a blog series that synthesizes and explains work in this area in a shorter format that is more accessible. And we have a community-driven wiki that is a living repository of work at the intersection of climate change and artificial intelligence. To stay updated on funding opportunities, submission calls, and announcements and job offers, you can sign up for our newsletter, which we send out every month. You can find all of this information as well as other kinds of CCAI projects, such as the CCAI happy hours, on our website, climatechange.ai. That brings us to today's discussion. There are hundreds of solutions to protect our planet, but many of these are too expensive and labor-intensive to be applied at the necessary scale. Building on lessons from manufacturing, many have started to explore the efficacy of robotic automation for climate change solutions. These applications range from scaling reforestation with drones to building solar farms with robots. This webinar will discuss specific applications of machine learning in the field of robotics for climate applications in conservation, restoration, and climate change mitigation. In particular, we will discuss the application of machine learning to coral reef monitoring and restoration, and machine learning to enable autonomy within floating seaweed farms. Our main question here is, how can machine learning and robotics help us scale climate action? To help us think through this critical question, I'm excited to introduce both of our speakers. Serena Mu is a PhD researcher with the QUT Center for Robotics. She is an advocate for environmental health and conservation and is focused on how robotics can play a part in positive environmental change. She is exploring efficient and cost-effective environmental surveying processes to better understand and protect ecosystems. Among her recent research efforts, Serena has been instrumental in developing and deploying FloatyBoat, a robot that restores coral larvae to damaged reefs to speed up the recovery of climate change-impacted ecosystems. After Serena, we will hear from Marius Wigert. Marius is a Climate Change AI core team member and a robotics and AI researcher at the University of California, Berkeley. He focuses on applications to tackle climate change across system biology, ocean and agricultural robots, and human-robot interaction. Marius leads the joint project of Berkeley and MIT on navigating seaweed growth platforms by leveraging ocean currents and machine learning, and is working with the startup FICOS to make gigaton-scale carbon removal with seaweed a reality. I'd like to thank both of our speakers for joining us today to present on machine learning and robotics to scale climate action. The floor is yours, Serena.
Hello, thank you so much. Let me just share my screen. Cool. Thank you, Amanda. So as you said, I'm talking about robots for scaling reef restoration. This work is being done at Queensland University of Technology through the Centre for Robotics. So the first thing I need to talk about is what is coral reseeding. So coral regenerate in two ways, asexually, so when they split off and they grow, and sexually, which is dependent on this yearly mass coral spawning event. So what we do is we go to these areas and we set up these floating larval pools in situ. And then on the night of the mass coral spawning event, we collect the coral spawn from the surface and then we put them into the pools to rear. We usually have some marine biologists with us. And so what they do is they can kind of identify when the spawn has developed into a larvae phase, and that means they're ready to be settled onto degraded reefs. And so we do that. This is quite a man-hour heavy task, and that's why it's really important to scale this up. So with Floaty Boat, which is this beautiful yellow boat, we kind of have set out some objectives, which is that this robot, for this purpose, it needs to be portable. It needs to have real-time detection. We need to be able to field deploy this at the site. And another big one is that we need to be able to train other people, non-technical people on how to use and deploy Floaty Boat. So this is where Floaty Boat comes in. So on the night of the mass coral spawning, we attach this net to it. We basically drive it backwards and it can skim the spawn off the surface. And that way we can stay inside a main boat and bring the spawn to us. And then when it's ready to settle, we pour them into these 100-litre bladders. And we made this larvae-friendly pump where we are able then to pump the larvae over the degraded areas of reef. So why is real-time classification important? So there are, so here we can see that they're up here. These are substrates that are suitable for reef restoration. So this is the type of substrate where larvae will settle on and start to grow. Some examples when that won't happen is if you release larvae over soft coral, sand, algae, or rubble, it'll simply wash away. It won't actually settle. So here's what our setup looks like. So from the top, we saw the larvae bladder, we saw the larvae-friendly pump. Inside this pod, you've got a computer, and underneath there is a camera that is pointing to the degraded reefs. So we set these kind of lawnmower pattern paths over areas of reef that we've kind of scoped out beforehand, and we've determined that this is a good kind of area for this restoration to occur. And then as it is driving over the reef, it's classifying in real time whether or not what we're over the top of is suitable, and it'll turn the pump either on or off. So as a quick summary, we can see that we have training and test data from two completely different areas. They are both from the Great Barrier Reef, but very, very different latitudes. We were able to get a pretty impressive performance from all of the data sets and from combining the data sets. And so the reason why it is important to have this real-time classification is because larvae is actually quite valuable. So there's a limited amount that we can collect every time. It's quite a laborious undergoing. So it's quite important to treat the larvae as precious. So this is the trajectory over a particular reef on Lizard Island in the Great Barrier Reef. And you can see the paths that we took over the reef, and this has been overlaid over a satellite image. And so you can see that the classifier is saying not to turn it on over areas of sand. And so from the data here, we can see that especially on this Loomis reef, we saved about 53% of larvae from being distributed over unsuitable reef. Another method of using floaty boat is 3D mapping. So using the same camera as before, we do these same kind of lawnmower patterns, and we're able to use photogrammetry to create these 3D reconstructions of the areas. So one of the points that we made about scaling up is how can we take this to, you know, a whole nother level. So in terms of portability, when we were designing Floaty Boat, it was really important that it was lightweight and we can pack it down really quick, really quite small, and we could quite easily send it overseas. And so here we have an example of that. So we sent some floaty boats over to the Philippines, and we were able to kind of guide them to setting up the floaty boat and deploying the floaty boat in a mostly self-guided manner. One of the other things that we've developed is a tablet app called Sage. So each of the floaty boats are controlled via this app. This is important because it's quite an intuitive way to be able to deploy these robots. So there are three main elements with Sage. So you can create a mission, which means you can set the GPS locations over where you'd like the robots to go. The control is when you then set them off to the mission that you've planned. And then finally, we have what we like to call the reef restopedia. And the main goal of that is to kind of collect as much knowledge as we can. So instead of having emails and answering questions, that the reef restopedia is somewhere that they can search for the answers for any questions that they may have. So just to summarize, during the Lizard Island 2021 coral spawning event, Floaty Boat was able to cover about 22 times more area in terms of releasing the larvae than manual methods. We have a substrate classifier that performs at over 99% accuracy. And by using this classifier, we were able to save up to 53% of larvae during deployment. And we've also had the floaty boat being tested overseas by our non-technical colleagues. That is me. Thank you so much for listening.
Thank you so much, Serena. That was very enlightening. I encourage anyone who has questions, all the people who are watching us today, to send them to us. You can send them via the chat. We'll have all of the questions by the end of the webinar in our Q&A session. So questions for Serena and for Marius, please send them and we'll have them by the end of the webinar. We will hear now from Marius. The floor is yours.
Okay, give me 1 sec for sharing. Okay, that works. Okay, welcome everybody. I'm happy to be here. I'm presenting a joint work between my group at UC Berkeley and Pierre Lemosiau's group at MIT, and we're thinking about how to scale seaweed farming with robotics. And I want to start a bit with like motivating the problem. In this audience, we don't have to explain much, but if we don't do anything about the climate, we're going to get more to the world to the right, which means extreme temperatures until the end of the century, with big extreme weather events and a lot of extreme weather events, which will not be fun for the world. So what we need to do is 2 things. We need to stop burning fossil fuels, so we need to get down with the emissions. But we also need to start removing actually carbon from the atmosphere. And according to the IPCC report, we need to remove 100 to 1,000 gigatons until the end of the century. As a comparison, if you put all humans together, that's about 1 gigaton of mass, just all like 8 billion human people. So quite a lot of mass we have to pull out of the atmosphere. So that's where seaweed come in. Seaweed is like a pretty awesome natural carbon bonder. It provides food and shelter for countless marine animals, and it also grows incredibly fast. It can, in the beginning phases, it can double its biomass each week, and at some point it's going to be more sigmoidal, but we have a very strong growth. And typically it grows near shore, and when it dies, a part of the biomass makes its way into the deep ocean, where the carbon in this biomass is then stored for thousands of years. So the question one can think about then naturally is, what if we can scale this process to the vast areas of the open ocean? And if we look at the numbers, the oceans are super huge. So if we could grow seaweed on just 0.1% of the oceans, that could remove a gigaton of carbon per year, and we sink that seaweed. The deeper we sink it, the better. So the idea would be then of the startup FICOS I work with in my research is, can we have a fleet of these floating farms of thousands of them that continuously remove carbon from the atmosphere, at the same time regenerating our oceans, because they're a good food and shelter for animals as well. So we get kind of want to achieve this double goal. And now the question is, where does robotics come in here? If we can think about it, there's certain regions which are better for seaweed growth than others. That's like for the nutrient concentration, meaning phosphate and nitrate, but also sunlight. But there's also certain areas which we might want to avoid, like shipping channels or marine protected zones. And lastly, maybe there's certain areas where we want to be at a certain specific times. Like this is like some areas where there's exceptionally deep canyons. So the idea here is, can we sink the seaweed in deep enough canyons as possible? Because that makes sure that the carbon is removed out of the atmosphere for multiple thousand years and not just 1,000. So that's where the robotics problems come in. So now the problem is, doing that with classical methods is too expensive. And that's mostly because those farms are huge and clunky. You can think of them as the size of a cruise ship. So when you steer them through water with very, very powerful engines, you need about 1,000 liters of fuel per hour. And if we need so much fuel, then basically the whole point of growing seaweed to sequester it or even use it for biofuel, bioplastic, kind of is not worth it anymore from a carbon perspective. And that's then the idea comes in, okay, the power of the motor scales cubically with the velocity through it. So that's why we look at other sea animals who might have better hints how we can do that. And if we look at sea turtles, they actually navigate from the Gulf of Mexico all the way to the Canary Islands using almost no energy by hitchhiking strong, powerful currents. Like here in this picture, the Gulf Stream, this icon. So what we are working on in our research is, can we navigate these floating farms by hitchhiking in ocean currents? That's the idea. And how that looks like is, here's an example of that. We want to go from the red point to the green target area. And basically what we can see here as well is like our maximum propulsion of our farm is super low. It's just 0.2 meter per second. Currents around us are significantly stronger, like more 2 meters per second. But if we hitchhike on the flows, you should see this animation. Yes, now it works. We can actually, it's a bit baggy, but yeah, essentially we can use the naturally occurring nonlinearity of the system to mostly just like ride on the flows. And then we use the little propulsion we have, symbolized by the arrow, to strategically change currents. Like you can see that here, sometimes we actuate exactly in the opposite direction than where we want to go, because we have to be very strategic. And that's because we are underactuated. We means we are weaker than the currents, so we can't just go anywhere, but we have to be very strategic how we actually plan to actuate. And with that, we can not only get to we cannot get everywhere, but we can get to most places. And we can get there a lot faster than just using our slow propulsion. And the reason why that's interesting for seaweed farming is also that because of the scaling law of that we need energy scales cubically with the velocity through water. If we can navigate in an underactuated way by riding these currents with 0.2 meter per second versus 2 meter per second, we need 1,000 times less energy. And this less energy translates in less cost for these farms because they need smaller solar panels, smaller motors, just generally a smaller structure, less big batteries. And that reduces the cost of these farms by a lot, and thereby enables us to have these floating seaweed farms and grow these lots of biomass. Okay, so that was a problem setup. Let's go into a bit of the, yeah, okay, no, I'm too fast. Again, I'll quickly go over problem definition, then have some animations about our classic control stack, and then go into how we use machine learning to improve the performance in this challenging setting. Okay, here we go. So problem definition, navigation and flow. You have your seaweed farm, and then what happens is it has a state. We model it the simplest way to model it is to just model it as latitude, longitude. You can also add seaweed like mass or battery, like how much energy is left. But for simplicity here, I'm just introducing us as two-point state system. Then the dynamics, the change in X is like your actuation, U. When we just assume that we can go anywhere. We can actuate our motor almost anywhere. And then there's the big strong currents around us. And typically what we want to do in controls is we want to have a certain objective over the trajectory. That's this part here. So we minimize our policy function, like find the best policy such that this objective minimized. That can be minimize energy, travel time, maximize growth. We start at a specific point where we're at. This is one of the key parts, which makes this challenging. It's nonlinear time-varying dynamics. And we only have daily forecasts available, which means we don't actually know this term perfectly. There's a significant forecast error. And the forecast error is actually on the same order of magnitude as our propulsion, which means the forecast can be as much wrong as we can actuate, which makes this a pretty challenging environment. Maybe we have a get to a target position. This is also a key part. We're underactuated, which means our maximum propulsion is significantly lower than the current speed. And we might want to avoid time-varying obstacles. So that becomes a pretty complex optimization problem. But don't worry, I just wanted to highlight to make it specific for the robotics audience. So more broad overview, we have then these forecasts, which are solar forecasts, which are where the ship's going to go, which are ocean currents. We feed them into a planning algorithm, which operates in the cloud. And then via satellite communication, we actually communicate with our platform. And the platform has access to extra sensor information, like GPS, how much battery is left, seaweed, how much seaweed is hanging on the bottom. And it can use a local planning planner, which takes the global into account and activate its motors. That's like the high-level sketch here. Okay, so the classic control stack, which we started with first, is we first have to simulate it. So we have this forecast flow, and we have the true flows, and between them is the forecast error. So the system simulation then happens with the true flow, and when we use the forecast, which we get daily, to calculate these time to reach maps. And these time to reach maps, you can think about them as we get them via dynamic programming that tell you for each point, if you are here, and follow the optimal control from here onwards, how fast can you get to the target? So that's why you see around the target area, which is here. It's pretty hard to see here. And here's the start point in this small picture. Between here, it's always 0 because you're almost at the target, you're closer to it. And here it's like 90 hours in this case. And if you follow this gradient of this value function, which we get from dynamic programming, we always get the time optimal control. So then the idea is, can we use this time optimal control function, value function, from which we then abstract the optimal control. And we can do that continuously. So we don't do it once in the beginning and then plan open loop, but we calculate this value function. And then at each time step, we might land somewhere totally different than we thought we land, but the value function there still gives us the optimal control. And that is equivalent to basically time planning every time step, or replanning for the full time horizon at every time step. And that's the classic way in robotics to handle uncertainty, to do model predictive control. So by continuously always following this gradient, we essentially replan every time step where we go. That's the key idea here. Here's an animation how that looks like in an actual current field. That's the Florida Keys here. So this is how we get the value function. This is the fastest time to reach the target in hours. So you can see it goes backwards in time. Like dynamic programming, we like to solve things backwards. Now you have this value function, and you can use it then to like extract the optimal control by following the gradient. So now we're gonna play the same thing forward, and this is like giving us the optimal control and how we should actuate here. So that's a classical control stack, and we put it to a test empirically. Our task setup is we have a distribution of also missions like Serena. We have 1,152 missions in the Gulf of Mexico, and they're distributed over time and space. So we want to have this diverse currents as possible. And we know that all of them are feasible in hindsight. So if you know the true currents, you can reach the target in 2.5 to 4.5 days. That's kind of our distribution we tested over. And then the agent itself has a maximum propulsion of 0.1 meter per second. So here you see always the start point in red and the target point in green, target area in green. So that's just to highlight our task distribution. And I don't go in all the baselines, but I'll just compare it to a simple baseline, which is the straight line planner. We basically just always actuates towards the target. It performs surprisingly well with 78%. And our controller, which we call multi-time reachability, and applying that in closed loop fashion, performs at 82.3%. And the reason actually why straight line performs so good is if the target missions are short, 2.5 to 4.5 days, then most of the missions are already in a good flow towards the target. So if we extend our planning horizon, that basically we not only look 5 days out, because the forecasts are only 5 days long, but we look like 30 days out, this performance of straight line drops to like below 10%. So it gets a lot harder to reach the targets because you have to act more strategically the longer the time horizon. In this case, we didn't have any reasoning after the forecast, so that's why we only selected missions which are not longer than the forecast itself. Okay, and the reason why our algorithm actually performs not too crazy much better is like, yes, we are more strategic, but the forecast error is quite big. And in this case, it's like actually quite a lot bigger than our own propulsion. So the way then we can think about it is we want to use machine learning to improve that. Let's actually start with this one. So the classical control pipeline is typically you have a forecast system. The forecast gets fed into the planner. Planner extracts the value function, and then we apply closed loop. That's what we did before. So now the question is, can we do better than that? And the way we can do better than that is if we actually use the difference that we see in our operations of the platform to improve the current forecast. And here's how it looks like. The white line should be representing the trajectory of the farm. The blue line is the forecasted currents. But as we actually operate, we realize how we drift around. So that's the orange arrows. And there's a significant difference that we observe between the measured currents and the forecasted currents. And we can use that difference to potentially, like, it tells us something about the currents around us. So we can use techniques from data assimilation to take those observations and improve our forecasts and then feed that back into the planning system. So that way we reduce our error, especially around the platform itself, the forecast error significantly. And yeah, hopefully in that way improve performance. That's the idea behind this. Okay, here's our architecture for that. We call it a Gaussian process 3D UNet. So you can think about it here on the left. There's a current example, and you can see a trajectory here. So we get observations how wrong our forecast was at each time step. So what we do is we put those observations and we smooth them with a Gaussian process, a 3D Gaussian process. So then we can actually extract, okay, the mean of the Gaussian process is 0, the bias, because we think the forecast is the best thing we have at this point. But then we feed those observations in, and it'll tell us at some point, if I was here, the forecast was so and so much wrong. And then we can extract also forward in time. We fit it in like 3 dimensions, time and space. So we can also extract forward in time a certain error mean, and also like an uncertainty of how, yeah, essentially a standard deviation of how wrong the forecast will be in the future. We feed those 2 smooth measurements from the observations. So that the cool thing is now, however many observations we have, we can also feed it in the Gaussian process. We have uniform input to our neural network, and we can put these observations, the smooth observations and the forecast into a 3D UNet, and then get our improved forecast out. That's essentially the key idea here. And with that, we get basically a forecast error reduction by more than 30%, depending on the different scenarios. That's what we get. And we are currently testing that, like how much does it actually increase navigation performance. The experiments are not fully done yet, but we definitely saw, like we already see on small tests that we tested it on, improvement of 5%. Okay, so one other question you might ask is now, okay, one big bottleneck here could be that if we do this kind of pipeline system that we often like to do in robotics, we have our observations, the task of data assimilation is getting the best forecast as possible, and then we use essentially classic techniques like planning and control, and we assume the forecast is accurate, and then we like do closed loop control. So that's making a bit of assumptions that basically the improved forecast is, yeah, that this pipeline approach makes sense, and there's not any information that's missing. So another machine learning paradigm which we're currently investigating is, can we essentially do it by using end-to-end optimization? Like here, each one is optimized by itself, each module, data assimilation, planning, control, and not for end-to-end control performance. So what we then look into is, can we replace this box with deep reinforcement learning, and can just directly go from data assimilation to control output, or even propagate gradients backwards through data assimilation and improve how we improve our forecast by, yeah, essentially using those current observations directly. Can we adapt the base in the data assimilation with the propagated gradient backwards? So that's the key idea here. And the way we set it up, you can see this work is not fully done yet, so not full results yet, but what we currently have is we feed in the time to reach function, and we always cut it out around the platform itself, and then the forecast flow. We feed those in. They're both, this is like a 2D map, and this is like essentially 4D tensors, 4 because you have the X, Y time, and then you also have the U and V direction of the current, so it's a velocity field. And then should directly predict as the navigation action. And we simplify it to be like a discretized action space. The key challenge here is, though, that you have this nonlinear time varying dynamics, and reinforcement learning is pretty bad at that, especially if it's long time horizons. So what we do is we frame it as a dense task. If we just care about getting to the target, like kind of a success rate, then it's a super sparse task with random actions. You're never going to get there, so it's very, very hard to train. So what we do instead is we frame it as a dense task and say, you get a reward depending on how low you get on this time to reach function. So let's say you start at somewhere at 90. After 10 hours, you're at 80 hours. So you get a reward of 10, basically plus 10. And if you were later on like somewhere further away, then you get like a negative reward. That's kind of the idea. And we got it working, and we got like to pretty good, like 95% performance in a simple case of 2D missions. And we're currently running it for longer and experimenting in the full complexity case for 5 days. And then we want to extend it further out to even longer time horizons. So that's how we bring deep reinforcement learning into the picture. And the last way we use machine learning, and probably going to go through this a bit quicker because we're running out of time, is especially for reinforcement learning to make sense, you need to have a good task distribution, which means we properly need to model the difference between the forecasted flow and the real ocean currents. And we have a proxy for that right now, but it's good enough in terms of the order of magnitude, but it's quite, it's not perfect. And you cannot just simply apply Gaussian noise because those things are not, the error is not random, but instead it's spatiotemporally correlated. Like if I'm wrong here in a certain way and like a certain buoy drifts to the north, the next time step, it will not, like in a Gaussian way, push to the other direction. Like it's not IID. So then the idea is like, here's like from HICOM, which is one of the forecast systems we use. There's like about 1,000 of those buoys in the open oceans called from the Global Drifter Project, and they give us measurements. So the question is, can we use those measurements to fit essentially a generative noise model that's more realistic, such that it matches the error statistics that we actually observe with those buoys? So that's the idea. Here's a bit of animations of that, forecast ground truth. And the idea is, can we use deep generative models, all the improvements in GANs and diffusion models these days, to estimate the forecast uncertainty? That's one way we can use that. This generative noise model, and generate realistic simulations. And here's how we do that. We essentially train a conditional GAN. It's conditioned on the forecast flow. You have like some C and backbones to make that 4D tensor not too scary, and some latent vector that we can ensure randomness, and we can generate new things. And then we train it on sparse buoy observation data. That's kind of a challenge we're currently investigating. And we see some promising results. Here's like one of them, where we get out a spatiotemporally correlated noise, which is also physics realistic, because we are exploring also to like basically enforce physics losses in that, to not have currents go against each other. So what you see here is basically spatiotemporally coherent noise. You can see like those fields moving around in space and time, across time, and they're not abruptly changing too much, unless my video is laggy. So that's the third way we bring in machine learning in the picture to improve that performance. Okay, concluding now a bit. What we see is we can fairly reliably now navigate by hitchhiking ocean currents, using classical control in combination with machine learning. So combining the best of both worlds, where each one of them is good at. And machine learning is specifically good at dealing with this uncertainty and dealing with high dimensional data, but not necessarily with long time horizon tasks, that where the control comes in. And we are actually very hopeful about this application, because if we enable this paradigm of navigating the hitchhiking ocean currents, it can also enable other applications, such as floating solar farms, which then store the energy in synthetic fuels so that tankers can come and pick it up, which people talk about in literature, but anchoring is too expensive of those things. Or even navigating balloons and wind, which is actually similar what the project Loon did. And they had algorithms to do it for station keeping and navigation as well. And with that, also wrapping it up and giving back to Amanda.
Thank you so much. That was so interesting. Now we have some questions for both of you. I'd like to start with a question from myself. The main theme of your talks was the use of machine learning and robotics technologies to scale climate action. We know that climate action and biodiversity conservation are closely linked, and that the oceans are a particularly relevant ecosystem that's very endangered. What role do these technologies, so both for Marius and for Serena, the technologies that you have shown us today, what role could they have in biodiversity protection in aquatic environments?
Serena, you want to go first?
Yeah, sure. So obviously we know that coral reefs are a very important element of ocean diversity. So a big part of our goal is to, we've kind of used this method in reefs where we have done the larval restoration and maybe about 4 years ago, and now those reefs are now sexually reproductive. So they are spawning themselves and growing kind of on their own as well. This is kind of very specific to reefs in terms of a broader ocean biodiversity. We have been talking with other groups about using Floaty Boat with the 3D mapping capability, largely on a surveying type setup. So we can, because it is so cheap and easy to use, we can send it back to the exact same locations over and over, and we can see how those areas have changed over time. And that's kind of used as a tool for other groups who are, you know, observing different types of underwater life.
That's really cool. Yeah, I really like the floaty boat idea. From our side, so there is biodiversity benefits because seaweed is basically providing food and shelter for a lot of animals. So there will be some. Although the application we are looking at is less directly linked to restoring biodiversity, the main aim is produce as much biomass as we can, essentially creating a new biological niche on the open ocean where currently seaweed cannot grow by having these floating farms there. And yeah, so yeah, I think it's going to be beneficial. The oceanographer we talked to say it's going to be beneficial for the ocean. We got those co-benefits. But there's also not too many animals outside on the open ocean to would snack on it or would like find a new habitat there, because there's also other reasons they want to be near shore. So there will be some co-benefits, also deacidification, but at the end it's more engineered towards getting as much CO2 out of the atmosphere as possible.
Thank you. Now we have some questions for Serena. We have two questions. Where have you taken the robots, and where do you plan to take the robots? And are there other applications that the floaty boat can be used for?
So first question. So yes, so we've used the robot for the reef restoration in a number of reefs. So there are 3 reefs on the Great Barrier Reef in Queensland, where we have taken it and used it and deployed it for this task and over a number of years, so at different times. And we've also taken it to the Philippines, where it's been deployed as well. Next year, we are planning to take it to Vietnam, the Maldives, the US Virgin Islands, and we are currently looking for other groups to work with where we can go as well. So hopefully lots more places. The second question, other applications for floaty boat. So we actually have had some friends from the CSIRO, which is another agency that we've lent some floaty boats to them, and they have a number of extremely expensive sensors. So things like rhodamine sensors, dissolved oxygen, turbidity, all these things. They basically just strap it to floaty boat, and then because it's so easy to program where to go, and it's also very good repeatability, because you can just plan the mission once and then you can run the boat there again. Their kind of current methods with sans floaty boat would be to take kind of a boat that you physically drive out there with these sensors. So it kind of is a lot heavier and a lot more expensive. And so that's why kind of floaty boat is so much easier to use. And yeah, like I mentioned, the repeatability has also been really valuable as well.
Great, thank you. We also have a question from YouTube by Pierre-Olivier Simonard. I believe it was during Mario's talks, but I think it's applicable to you both. What are the programmatic tools used for your machine learning models?
Yeah, I can take that. For us, it is, we use potentially PyTorch and train it for that's for our generative, both our generative models and for the data assimilation machine learning. And yeah, we then use weights and biases to just optimize our experiments, do hyperparameter tuning, and yeah, do all that kind of things. For the RL, we use RLlib as it's quite a lot easier to set up than building all the RL pipeline yourself.
Very similar. We use PyTorch mostly, and weights and biases as well. Both really, really great tools. Highly recommend. Very easy to use. Yeah.
Great, thank you. We have a question for Marius from Zoom from John Wells. Do you or could you perform the path planning optimization for each member of an ensemble forecast? And if so, should you formulate the ensemble cost function?
Yes, that's a great question, John. We're actually looking into that right now. So right now we don't actually have an ensemble forecast yet. Basically for weathers, they do it because ensembles are very costly to calculate because they need to run their physics PDEs on the supercomputers a lot of times to get these ensemble forecasts. So the weather systems, for weather they do it, but for ocean currents it's not important enough. So they only give us a deterministic forecast at this point. And that's one of the reasons why we use this generative model to model this uncertainty. And once we have that running well enough, I think we're right now essentially getting there, and we're looking into how can we use it to not only get a deterministic value function, but have a stochastic value function that encapsulates the stochastic best time to reach and make it a stochastic optimal control problem. Yes, I think that's one of the most promising areas for going into the future. Yeah.
Thank you. We have more questions. So that is an interesting application of robotics. How did you find out about this application and put your research in that direction?
Yeah, that's a good question. Yeah, basically it was a lot of coincidence. And like I was looking for, before I was working in human-robot interaction and in using control theory for in systems biology to improve cancer therapies. But I really wanted to find a climate application for my work where I feel like my work is useful for, basically climate change. And I was fortunate enough to do an internship at Google X and met the founders of the startup Pipos there. And they discussed with me their idea about having these floating seaweed farms out there to scale seaweed farming to the open ocean and produce lots of biomass. And then basically the question was, okay, how do we navigate these farms? And you roboticists, like, what can you do, essentially? And basically we came up together with the idea of, can we use the ocean currents to hitchhike around? And I looked in the control literature. Is there anything we can already there for nonlinear time varying control under actuated situations? And turns out there was not as much as I would hope for. And then wrote a grant proposal, got some funding for it, got like the lab at MIT, Pierre Lemosiaux involved. He's an oceanographer. And so it's a lot of coincidences that led me to this point. And now I'm very happy that I found a project like that for my PhD.
Thank you. And how do you think about including safety as an objective in this challenging environment, especially when using reinforcement learning?
Oh yeah, that's the challenge with reinforcement learning being not very interpretable. That's definitely hard. We're currently thinking about it in terms of essentially a switching, or you can think about it as a safety filter or switching controller. That's how we like to think about it. So you have your main control system and it optimizing the objective, be it like maximizing seaweed growth. In this case, as I showed, be it navigating to the target. And then we have a simultaneous system that estimates the probability of constraint violation until a certain time in the future. And we have a way of calculating that right now. We're still improving that. But once we have this certain probability of constraint violation, if it reaches a certain threshold, we basically switch to our safety controller, which means we just ignore our performance controller, being at our elbow, being something else. And our only goal for the platform is just get yourself to a current that will not drift you in a marine protected area or like a shipping lane. So we have this, like the way we think about it right now is having this switching controllers, one estimating this probability of constraint violation, that the currents push you somewhere, like be it on an island or something where you don't want to go, and then switching that over, like using that as a switching criterion, and then having the safety controller, which only goal is to get away from that as fast as possible.
Thank you. We have a question for both of you. If you would want to experiment on machine learning tasks in these areas, are there any open datasets or tutorials available online that you could recommend?
I can start and then hand over.
Yeah, go for it.
Yes, so we built our simulator from scratch, and it's almost good enough to be open sourced. I want to open source it basically until the end of the year, beginning of next year. Yeah, and then hopefully get more people from the community involved to work on that problem or use it for other things, for navigating in the oceans. So I think there's definitely opportunity to get involved there. So far it's not open yet, but it's going to come soon. Serena.
There are so many online tutorials. So both of us use PyTorch. PyTorch is really well documented. If you kind of have an idea, you could, I'm almost certain PyTorch will have a tutorial for you to follow, including data sets. Our data sets are not online, they're not open source. But in terms of classifiers, there are plenty of data sets that you could find available online.
Great, thank you. I'd also like to address a question by Grace Silas Asa on the Zoom chat. Very interesting. With the challenges we are facing, robotics seems to be a way not to be overlooked in conservation. Thank you for this rich moment of knowledge sharing. We hope to have the slides at the end. So yes, you have all of this presentation, including these slides, available at YouTube. It will be on the Climate Change AI channel on YouTube. So it will be available for everyone. If we do not have any further questions, this could be a good place to wrap it up. We want to encourage everyone to continue the conversation on the Climate Change AI community and brainstorm potential new applications and ideas on machine learning and robotics to scale climate action. I'd like to ask our speakers if they have any final remarks.
Yeah, I think from my side, my final remark would be, if you're in robotics, I think there's not many people in robotics working on climate change applications, unfortunately, and I think it should be more. And I think it needs some creativity to like engage with domain experts, see what their problems are, and then you can find applications. I think that's, basically would encourage people to reach out to domain experts, get involved in the community, see where the problems is, what currently are they doing manually, which would or is too expensive to do, where robotics can get involved. And from the machine learning side, probably similar if you're like machine learning and apply to like physical ocean restoration, not only satellite monitoring. I think there's also great applications for that.
I absolutely agree. Just to kind of carry on from that. So I do a lot of traveling. I go on a lot of field trips with this project. I work with a lot of marine biologists specifically. There are so many processes. I wish there were 10 of me. There are so many potential projects out there in terms of being to support ecologists, marine biologists, yeah, they're all doing such amazing work, but there are a lot of tasks that are very kind of manual, very, you know, man-hour heavy that could be, you know, alleviated with machine learning and AI. Yeah, and thank you for having me. Very, very glad to be here.
Thank you. Thank you for your time and your presence. I'd like to reinforce what our speakers have said and invite you all to exchange these ideas on climate change AI's networks and communities, and invite you all to stay tuned for future CCAI webinars. Thank you so much, Serena. Thank you so much, Marius, for your time and your contribution in this area. And thank you so much for all those who joined us today.
Yeah, thank you.